So, hello everyone, I'm José Santos. I'm presenting JaVerT. JaVerT is a JavaScript verification toolchain based on separation logic that I developed at Imperial College London together with Petar Maksimović, Daiva Naudžiūnienė, Thomas Wood, and Philippa Gardner. And here we are. And Petar is here, Philippa is here, so if you want to talk to us about the project, come. We'll be delighted. So why JavaScript? Well, JavaScript is a highly used language. It is the language of choice for implementing client-side web applications. In fact, it is the most used language on GitHub. It is the most asked about language on Stack Overflow. So I think that's a valid reason. So what is JaVerT? JaVerT is a verification tool for JavaScript. It is semi-automatic and it is based on separation logic. JaVerT is aimed at a specialist developer wanting rich, mechanically verified specifications of critical JavaScript code. And in this talk, I will address the challenges that we faced in developing JaVerT. In particular, I will focus on three main challenges. A specification challenge. We wanted JaVerT specifications to be readable by JavaScript developers. A verification challenge. We wanted JaVerT to tackle the full complexity of JavaScript without making any simplifying assumptions, without departing from the letter of the standard. And a validation challenge, how to validate the construction of the tool. So those are the three main challenges that I will be addressing. So I will start by focusing on the verification challenges, and I will divide this challenge into three sub-challenges. So basically, JaVerT needed to tackle the complexity of the JavaScript statements. JaVerT needed to cope with the fundamental dynamic behavior of the language, and JaVerT needed to be able to reason about JavaScript internal functions. And having said that, so we can see the overall structure of JaVerT. So it receives as input a JavaScript program annotated with pre and post conditions, annotated with loop invariants, and folding and unfolding instructions for handling user-defined recursive predicates. The first thing JaVerT does is to compile the JavaScript program to JSIL. JSIL is our intermediate language for JavaScript verification. It also compiles the JavaScript logic assertions that annotate the program to JSIL logic assertions, and then we obtain a JSIL program annotated with JSIL logic assertions. This program we give to JSIL Verify. JSIL Verify is our semi-automatic verification tool for JSIL. JSIL Verify also receives as input the axiomatic specifications of the JavaScript internal functions. So, as we know, so for those who are not familiar with JavaScript, so in the standard, the semantics of even the most basic commands is described in terms of these JavaScript internal functions, which is like, for instance, get value or put value. This means that the behavior of even the simplest command, like an assignment, may correspond to hundreds of pathways through the standard. So we have written axiomatic specifications for these JavaScript internal functions, and these axiomatic specifications are also given as input to JSIL Verify. So given an annotated JSIL program and the axiomatic specifications of the JavaScript internal functions, JSIL Verify checks whether or not this program satisfies its specifications. We have taken great care in validating all the elements of this infrastructure. The code produced by the compiler follows the standard line by line. The compiler has been thoroughly tested against the official ECMAScript test suite, and we have proven correct the fragment of the compiler. We have also proven the translation of assertions correct. We have proven the JSIL logic sound, and we have proven that the axiomatic specifications of the JavaScript internal functions are satisfied by the reference implementations. Now I will focus on the first verification challenge, so the complexity of the JavaScript statements. So the complexity of the JavaScript statements renders building a program logic directly on JavaScript infeasible. We deal with this complexity by compiling JavaScript to JSIL, which is a very simple language. So the complexity of the JavaScript statements does not go away. It is simply moved to the translation. That is the main message here. So I will not talk about the coverage of the compiler, so you can see it on the slide. The compiler has extensive coverage. It supports all the constructs of the language and most of its built-in libraries. We do not support the date library, the JSON library, and the regular expression library because they are orthogonal and also because we judge them to be the boundary of our very much academic project. However, we can extend the compiler to the full JavaScript language by following the methodology that we applied for the other libraries. So, as I said before, we have thoroughly tested JS to JSIL, our compiler from JavaScript to JSIL, against the ECMAScript official test suite, test 262. We have developed continuous integration testing framework that allows us to run all of the tests quickly, precisely understand which tests are failing and why they are failing. This framework also allows us to efficiently filter out the non-applicable tests. In the end, we have identified 8,797 appropriate tests, of which we pass 100%. So we normally say that we pass all the tests that we are supposed to pass, and we know why. So, as I said before, so the JaVerT translates the JavaScript program to JSIL, and it also translates the JavaScript logic assertions that annotate the program to JSIL logic assertions. So if we combine these two translations, we obtain a translation from JavaScript logic triples to JSIL logic triples. A thing that I would like to say here is that the logic translation is really straightforward because the JavaScript the JSIL memory model coincides with the JavaScript memory model. So this translation is very simple. And so we have proven that under the assumption that JS to JSIL is correct, if we are able to verify a translated JavaScript triple at the JSIL level, this triple must also hold at the JavaScript level, meaning the original triple must also hold at the JavaScript level. So I'll now move on to the second verification challenge. And this has to do with a fundamental dynamic behavior of JavaScript. So the fundamental dynamic behavior of JavaScript does not go away with the translation. JSIL Verify needs to handle this. What is the this? The this is the dynamic properties, the extensible objects, and the dynamic function calls. So this fundamental dynamic behavior renders the frame inference problem more complex in this setting than in the standard static setting. So JSIL Verify, you can see the structure of JSIL Verify on the slide. It comprises a symbolic execution engine that symbolically executes JSIL commands on JSIL logic assertions. This symbolic execution engine makes use of an entailment engine. The entailment engine uses pattern matching for solving the spatial part of the entailment and discharges the pure part of the entailments to the Z3 SMT solver. And that's essentially, and you can learn more about JSIL Verify on the paper. So the last verification challenge has to do with the JavaScript internal functions that I've talked a little bit before. Basically, here what we have done was we wrote axiomatic specifications and reference implementations for all JavaScript built-in functions, internal functions, I mean. And we have used JSIL Verify to show that the axiomatic specifications that we've written for these functions are satisfied by the reference implementations. And it's important to say that these reference implementations, again, follow the standard line by line. So this gives us trust that these axiomatic specifications really capture the behavior of the JavaScript internal functions, which are described operationally in the standard, not axiomatically. So using these axiomatic specifications of the JavaScript internal functions, JSIL Verify can jump over their reference implementations during verification. So we don't have to symbolically execute the reference implementations of the JavaScript internal functions. We can just use their axiomatic specifications. So now I'll move forward to the verification, to the specification of JavaScript programs. And here we highlight two main challenges. So we would like JaVerT to provide abstractions capturing the key JavaScript concepts, such as prototype-based inheritance, variable scoping, function closures, and so on. But also abstractions that hide the JavaScript internals. So we don't want the program to have to know all the JavaScript internals in order to specify its own programs. So, and we have developed abstractions for both purposes, and I will illustrate the use of them with an example of a JavaScript implementation of a key value map. So here is the code of the example. So this is a simple implementation of a key value map. We have 4 functions: a function map for constructing new map objects, a function get for retrieving the value associated with a given key in the key value map, a function put for inserting a new key value pair into the map or for updating the value of an existing key, and a function valid key to determine whether or not a given key is valid. So, and we can see that even this simple example already exhibits lots of JavaScript specific features. So for instance, we have extensible objects, we have prototype-based inheritance, we have dynamic property access, and more. So now let's look at the example in a bit more detail. So we can see what is a map object. A map object is an object with a property contents that points to the object contents. And this object contents is the object that stores the key value pairs. So if we look at the slide, we can see that the contents object has the key value pairs K1, V1, K2, V2. The keys are the properties. The values associated with the keys are the values of the properties. So then, the functions shared by all map objects are stored in map.prototype. So we have in map.prototype get, put, and valid key. And now, and map.prototype and object and the contents object have both prototype object.prototype, which is the usual end of prototype chains in JavaScript. So now let's try to break the behavior of this library. So one way of doing that is by creating a new map object and setting the property get of this map object to an arbitrary value. If we do this, we no longer can invoke the get function on the map object. So a good map specification should disallow this behavior. This means that when specifying JavaScript libraries, we need to be able to state which properties should not be present in a given object. Not only the properties that are present, but also those that cannot be present in the object. And here, so, we know that the properties get, put, and valid key should not be present in map objects because they are to be accessed in map.prototype, not in the map object. So another way to break the behavior of this library is to define in map.prototype a non-writable property that is to be found in the map objects. For instance, here we know that map objects contain the property contents. So if we define in map.prototype a non-writable property contents, we can no longer invoke the map constructor without causing an error, because in the body of the map constructor, we see that this .contents is assigned to a new object, and this assignment will fail if contents is non-writable in the map.prototype. So now I'll show so we see that contents must not be writable in map.prototype and object.prototype. So I'm going to make an aside comment. I think I forgot to say that the way we specify that properties are not writable is by setting them to none. So none is the special logical value that you use to state that the property is not writable. So I apologize. At least now it's clarified. And so the third way of breaking the behavior of this library is by inserting in a map a key value pair with key as on property. If we do this, we break the behavior of the get function, because the get function expects to find the function, uses the function as on property of object.prototype to check whether or not a given key is in the map, is already in the map. So if we insert as-on property in the contents object, we will no longer be able to invoke this .contents.asOn property. Yes, thank you. So here we see we have to state that as-on property is not present in the contents object. So summarizing, we can say that constructed objects cannot redefine properties that are to be found in their prototypes, and prototypes cannot have non-writable properties that are to be present in their instances. We call this specification paradigm prototype safety. So applying prototype safety to the map example, we know that map objects must not contain get, put, and valid key. Map.prototype and object.prototype must not contain contents as a non-writable property, and the contents object must not define the property as on property. So now we can look at the specification of what is a map object in JS logic. I will not explain this specification in detail. We can see in red that a map object at address M with prototype MP and key value pairs KVS. M cannot have the properties get, put, valid key. The contents object is denoted by that C, and we see that the contents object cannot have the property as on property. A thing I would like to denote about, to highlight about this example is that it uses two abstractions, JaVerT built-in abstractions, as I call them. A JS object denotes the internals of a JavaScript object, and data property, and data prop denotes the internals of JavaScript data property. So given a predicate that describes what is a map object, a predicate that describes map.prototype, and the predicate that describes object prototype, we can specify the get function. So here in this slide, we see three specifications corresponding to the following cases. The case in which the key value pair exists in the map, the case in which the key value pair does not exist in the map, and the case in which the key is not valid. I will briefly talk about the case in which the key value pair exists in the map. It is the top left case. So we can see that we want to retrieve the value associated with key K from the map object. And we have a map object at the Ds with prototype MP. The prototype is a valid map prototype, and we also have the resource corresponding to the object prototype. Because we have KV in the set of key value pairs of the map, this method returns V and leaves while leaving the resource of the precondition unchanged. So we have the spatial resource of the precondition, and we return the value V, which is the value associated with the key K. So we have used JaVerT to verify JavaScript implementations of commonly used data structures. We have verified binary search trees. We have verified linked lists, singly linked lists, doubly linked lists, priority queues, key value maps, and others. The times are not very bad, I think, given that the small JavaScript programs are compiled to hundreds of lines of JSIL programs because they correspond to, well, due to the complexity of the language. There is not much work on logic-based verification of JavaScript programs. The nearest related work to ours is KJS. KJS is an instantiation of a general verification framework to JavaScript. However, KJS specifications, it does not provide built-in abstractions to reason about the JavaScript internal. So if you want to use it to specify your JavaScript program, you really need to understand how the semantics of JavaScript works. Also, KJS is considerably slower, and it lacks examples showcasing JavaScript-specific features. So I conclude with future work. So dark blue boxes correspond to the work that has already been done. These POPL papers are not all mine. They are, but they come from my group. And the light blue boxes are the future work. As I was saying, currently I'm working on Cosette. Cosette is bug finding tool based on symbolic execution for JavaScript, and I'm particularly interested in the use of Cosette to help debug not only programs, but also programs and specifications, because the output of JaVerT can be quite daunting to read. So, and this concludes my talk. Thank you.
Hi. Congratulations. Perhaps my thinking is too naive, but is this framework that you have developed, couldn't it be used in a much broader sense, not only for prototype-based language to verify what's actually, even language like Python that you have, it seems that you have the infrastructure and the power to do that, because it's still, you need to check the properties and validity of them.
So, well, I had memorized the sentence that goes more or less like this. So we believe that, so we believe that the main ideas of this project can be applied to the verification of other real-world, highly complex dynamic languages. I think that the difficulty is to write a compiler from that language to JSIL, but I really think that JSIL is expressive enough to easily model all these, the behaviors of all these dynamic languages, certainly.
Okay, thank you.
Impressive work. I have a question and a comment. The question is, have you tried to verify properties of large JavaScript libraries like jQuery, or and I know of some other static analyses that manage to do that, obviously not using a logic, but their own custom analysis. But is there a comparison there?
So we are in the process of doing that. Basically, our priority queue example comes from a priority queue implementation that we found in Node in the NPM package manager. We simplified it a little bit in order to be able to verify it, but we are actively working on that.
Okay, and the comment is that because you seem to need annotations on JavaScript programs in order to be able to analyze them. Nowadays, ES5 is more or less the target language for JavaScript, and most people write ES6 or ES7 or even other experimental features. And if you have to verify source programs, I suppose you should extend this to support newer versions of the language.
Agreed.
Cool paper. So here you talked about the straight line code validation, but there's an awful lot of asynchronous programming going on in JavaScript. So I was wondering if you had a story about how you'd expect to handle any like event-based programming or programming with callbacks.
So my view on that is that this is the first step towards a verification tool for JavaScript in the wild, in the a semi-automatic verification tool. We are currently working on extending JaVerT to higher order reasoning. I think higher order reasoning is essential for reasoning about events, given that events have these continuations and you don't want to reason about a particular continuation. You want to reason about continuations that have a certain behavior. So I think we will do that when we get higher order reasoning to JaVerT.
Thank you.
Yeah, this is a pretty good paper. So one thing I notice is, or one thing I think about is that the JavaScript memory model is very similar to what you have for either Python or PHP. So have you thought about expanding this system to Python and PHP?
Yes. We are talking, one of our colleagues at Imperial is a specialist in PHP semantics, so we are, and we've been talking about it. Yeah, that would be nice, but the thing is that we are just 5 people, 3 or 4 people, so it's there's much to do. And
hopefully it happens in a couple of years.
Yeah, thank you.
Yeah. Okay, thank you.